So let's try everything together in a problem. We want to know when something is increasing, decreasing, and find any local or relative extrema of a given function. Again, we're going to follow the process created by the sign chart method. The first step of the process is to find the derivative and those critical values. Well, if I look at the derivative of this function using our simple derivative properties, I'd have 6x squared minus 6. Again, to find critical values, we want to set that equal to 0, and as this is a polynomial function, this is never undefined. Solving this equation, let's see what we get. We'll add 6 to both sides. I end up with 6x squared equals 6. Divide both sides by 6. I have x squared equals 1. Taking the square root, never ever forget plus or minus when you take the square root of a square. And I have x equals -1 and 1. I look back at the original function. I consider those points, those values into the original function. They are defined, so indeed these are our critical values or our critical numbers. I'm going to draw my number line. I'm going to put down these critical numbers, -1 and 1. I'm going to consider the derivative at these, and from that be able to interpret what happens to the original function. We already know the derivative is 0 at both -1 and 1 because that is what we solved for. We need to consider the remaining intervals, -infinity to -1, -1 to 1, and then 1 to infinity. We do this by creating a sign chart, which is step 3. We're going to plug this into the derivative of the function. The derivative of the function was 6x squared minus 6. I need a test point in each one of the intervals. The first interval was -infinity to -1, so I'll choose a test point of -10 for that interval. We continue on and look at the next interval, which is -1 to 1. I'm going to choose the point x equals 0 for that interval. And the last interval is 1 to infinity. I'll choose the point 10. Again, these are arbitrary numbers that I've chosen. You can pick any number you want as long as it's in each of those 3 given intervals. When I plug in -10, -10 squared is +100 times 6 minus 6 is a positive value. When I plug in 0, I'd have 0 minus 6, which is a negative value. When I plug in 10, I would have, once again, 100 times 6 is 600 minus 6 is a positive value. So on the entire first interval, because my test point was positive, it has to be positive. On my second interval, because the test point was negative, that entire interval is negative. And on the third interval, because that test point was positive, that entire interval must be positive. We go back to thinking about what we did in the previous section. We know anywhere where my derivative is positive, my function has to be increasing. Then I have a critical value. My derivative is negative, so my function is decreasing. I have a critical value. Then my function is increasing. If we look at these points, what must happen at that point? Because it goes from increasing to decreasing, that means this point is a maximum. And here, because it goes from decreasing to increasing, it means this point is a minimum. So, intervals of increasing, trying to put this together, intervals of increasing, we've already determined it's increasing from -infinity to -1, and it's also increasing from 1 to infinity, so I'll write that now. We want to look at intervals of decreasing. When we were looking at decreasing, we determined it was decreasing on the interval -1 to 1. And now we need to look at the local maximum. Here it's just asking for a maximum and a minimum. A maximum and a minimum occur at a point. It might want just the x value here, just the y value here, or the actual point on the graph. It's not clear to me which one this one wants, so what I'm going to do is actually include the full point. I know the maximum occurs when the x value is -1, and the minimum occurs when the x value is 1 from drawing conclusions from our sign chart that we created. So now what's left is I have to find the y values of those points. How do I find the y values of the points? Is I need to plug those critical numbers, that -1 and that 1, into the original function. So I'll do that now to determine the associated y values. When I plugged -1 into the function, I ended up with a y value of 5. And when I plugged 1 into the function, I ended up with a y value of -3. That allows me to come back here and finish off the problem. The maximum occurs at the point -1, 5. The minimum occurs at the point 1, -3. So I have my intervals of increasing, my intervals of decreasing, my local maximum written as an ordered pair, my local minimum written as an ordered pair. This process is the exact same anytime a question asks for increasing, decreasing, and local extrema. If we're using the first derivative test, we're going to follow this exact same process. Find the derivative, find the critical values, plot them on a real number line, test points in each interval, interpret increasing and decreasing. If it changes from increasing to decreasing, it's a max. If it changes from decreasing to increasing, it's a minimum. That allows us to get the final answers. Just remember, you do need to plug those critical values into the original function to find the y values, so you can write the local maximum and minimums as ordered pairs. So let's take a look at the next problem. I've already worked it out for us, but let's see if we could understand what happened. Again, it was increasing, decreasing, and local extrema for a function. The first thing we did was found the derivative, which would be 4x cubed minus 12x squared. We set it equal to 0 or undefined to find the critical values. This is a polynomial, so it's never undefined. When I set it equal to 0, I got two critical values of x equals 0 and x equals 3. Those are critical values because they are defined in the original function. I drew my number line. I plotted the numbers 0 and 3 on the number line. I determined my first interval was -infinity to 0. My second interval is 0 to 3. And my last interval was 3 to infinity. I go ahead and created my sign chart over here. I plugged x values into the derivative. Notice I used the factored form of the derivative because that's easiest to determine the sign. I picked a number between -infinity and 0. I picked -1. I saw that it was a positive times a negative, which is negative. Because it was negative at the test point, it had to be negative on that entire interval. I picked a test point between 0 and 3. The number I picked was the number 1. Plugging the number 1 in, my first factor was positive. My second factor was negative. Again, a positive times a negative is negative. And because it was negative at that test point, the entire interval must be negative. I looked for a test point between 3 and infinity. I picked the number 4. Plugging the number 4 in, I got my first factor was positive. My second factor was positive. And a positive times a positive is positive. Because the test point was positive, that entire interval must be positive. So now I look at it. Anywhere where my derivative was negative, I'm decreasing. Anywhere my derivative is positive, I'm increasing. That gives me my answer for increasing and decreasing. It was increasing on the interval from 3 to infinity. It was decreasing on -infinity to 0, as well as the interval 0 to 3. Notice, on this example right here, at this critical value of 0, my derivative goes from negative to negative. Because it's the same sign on both sides, I can't tell you anything about that point. It is not a local maximum nor a local minimum. But on this one, I go from negative to positive. On this one being the critical value of x equals 3, I go from negative to positive. Because I go from negative to positive, that's decreasing to increasing. I know that point is a local minimum. When I have a local minimum, so my local maximum is none, my local minimum, I know the x value is 3, but I need to write the answer as an ordered pair, so to do that, I plug it into the original function. If I plug 3 into the original function, I end up with -27, so my minimum is the ordered pair, the point on the graph, 3, -27.